Hi, and welcome to the third video in this lecture. In this video, we are going to continue our discussion of the peripheral nervous system and how we are testing for abnormalities in the peripheral nervous system. And we are going to look at what is called electromyography. Now, you must have heard of electromyography. It is usually known as EMG. And that can be used as well as a diagnostic tool to discover what is wrong with the neurological system in our body. So we've looked at this slide before, right? This is the peripheral nervous system, and the peripheral nervous system we said consists of two things: the sensory neurons and the motor neurons. Now the motor neurons end in a muscle, and the junction between the muscle and the nerve is called the neuromuscular junction. Okay, now if we look at the electrical activity that is produced by the muscle, which is the EMG or the electromyogram, we can figure out some of the problems that were happening before in the motor neuron and higher stages, right? Especially if you combine that with nerve conduction studies. So let's say you do a nerve conduction study for this nerve and you find out that this nerve is working all right. I mean, you can't find any abnormalities there. And you go to the muscle and then you find that something is wrong there. So then you know where to look for clinical problems, and you have kind of localized the problems and provided a diagnosis, isn't it? Now, the EMG that we are talking about is not EMG from surface electrodes. That is helpful, and we did those kinds of measurements in the previous video where we talked about compound muscle action potentials. In this video, we want to look at what is called needle EMG. Okay, needle EMG is EMG where you actually take a needle and put it into the muscle and then record EMG using that needle. The reason why this is very helpful is because when you cross the skin and you put needle into your muscle, you are able, first of all, to get much higher levels of electrical activity. So you can, because the skin barrier is removed. And secondly, the needle electrodes themselves have a very, small field from which they measure. So you can have two different kinds of needle electrodes. So one is the monopolar electrode, where you have a ground electrode outside on the skin and you record the active electrode is sent inside the muscle through this needle. Or you could have the bipolar needle, where the outside rim is a metallic plate which acts as a ground, and the middle one, there's a metallic core which acts like the active electrode. Okay, and the bipolar electrode has a kind of records from this area, right? And you can see at different positions it can record from different areas, while the monopolar electrode records from a much larger area. But both of these electrodes record from much smaller areas than a surface electrode would record, because a surface electrode is going to record from the entire muscle as such. But a needle electrode, because it's much closer to the muscle fibers, will record only from the muscle fibers around them and not the entire muscle. And that helps to give us some diagnosis. Okay. A magnified version of the bipolar electrodes are presented here as well. Now, what do we want to look at when we are looking at this? So when you put the needle electrode, what you're doing is you're actually putting your electrode near muscle fibers, which means that instead of getting the EMG for the entire muscle, you're getting the electrical activity of different motor units, right? Because you're putting your electrode close to a particular, let's say a particular muscle fiber which belongs to a motor unit, and you can record the potentials of those motor units. And what you can record is you can record the morphology, that is the shape of the motor unit action potentials. You can look at the stability of the action potentials. Is it coming stably or is it coming and going? Is the amplitude growing up and then going down? Things of that kind. And you can also look at the firing characteristics, how fast it is firing. Very slowly, very fast, is it regular, irregular, those kinds of things. Okay. One interesting thing about this is that when clinicians actually use needle EMG, one way you look at the signals is on the computer screen, of course. But many clinicians also convert this motor unit action potentials that you're recording into audio. And you can record, and as you get more and more trained, just listening to the audio, you can say, well, that looks like the action potentials are not very regular or irregular, or their shape is slightly different. I think there's something odd about it. Or, you just develop that skill of deciphering motor unit action potentials just from the sound that they produce. So just to remind, I've been using the term motor unit action potential. What's a motor unit action potential? So when the action potential travels down a motor neuron, it activates a lot of muscle fibers, not just one, right? We talked about that before. And when it activates a lot of different muscle fibers, all the muscle fibers then contract or generate activity at the same time. And the signal that is produced is called the motor unit action potential. When the muscle fibers belonging to a particular motor unit fire together, the electrical activity of that motor unit is recorded as the motor unit action potential. Okay, and that's what we are looking at when you're talking about EMG. Now let's talk about these motor units. We talked about the size principle before. Remember, we said that when motor neurons come from the spinal cord to the muscle, the speed of movement of the action potentials through the motor neurons depends on the size of the motor neurons. If the motor neurons are big, the action potentials are going to travel much faster. So if the neurons are large, the axon is large, the myelin is thick, the conduction velocity is very fast. But at the same time, it is more difficult to actually activate that particular motor neuron. Okay, that's why the threshold is very high. And the fiber type is type 2, which is basically a fatigable motor neuron. Or the fatigue is related to the motor unit, not the motor neuron, but still. Okay, and similarly, you have medium-sized and small-sized motor neurons. Now, what you want to test when you're putting needle EMG, one of the things that you want to test is whether the motor unit action potentials are normal. So you don't just put the needle once, but you want to put it a few more times so that you can create a distribution of the motor unit action potential duration and amplitude and make sure that everything is normal, right? So in a normal person, the motor unit action potentials are kind of distributed normally, and the amplitude distribution looks like this. And what a clinician would do is he would record motor unit action potentials from a variety of places in the muscle and try to see whether some abnormality has happened in the duration and amplitude of the motor unit action potential. Now, what kind of abnormalities can happen? Now, imagine that there are 4 motor units in a muscle, and these 4 motor neurons are bringing in the signals, and everything is fine. So you get an MUAP like this, right? But what happens if there is partial denervation? That is, one of the motor neurons has been disconnected from the muscle. Then you get a slightly different signal, isn't it? Because these motor units are not going to be activated. So when you are checking for motor unit action potentials at different places, you can say, well, I am seeing that the activity is much lower than what it should be. And so the clinician starts to know maybe there is some denervation going on here. Also, sometimes what happens is if there are some motor unit muscle fibers which are not innervated by a nerve, the adjacent motor neurons start to connect to those muscle fibers. And if that happens, then you get something like this. You get a motor unit action potential, and then you get a late spike in the motor unit action potential, which starts to suggest reinnervation, and you can detect that.